In this module, we are going to study a simple criteria for Riemann integrability. A consequence of this criteria is the fact that any continuous function will be Riemann integrable. In a later module, we shall study the Lebesgue integrability criteria that completely characterizes all Riemann integrable functions. So, theorem, let f from AB to R be a bounded function. Be a bounded function. F is Riemann integrable. F is Riemann integrable if and only if we can find if and only if for each epsilon greater than 0 we can find a partition p epsilon such that u f p epsilon minus L f p epsilon is less than epsilon. The proof of this is very straightforward. Proof. Suppose f is Riemann integrable. We will first deal with that direction. Suppose f is Riemann integrable. Then that just means that infimum of UFP is equal to supremum of LFP. That's the definition of a function being Riemann integrable, which just means that we can find partitions P1 comma P2 such that U of FP1 minus L of FP2 is less than epsilon. Why is this the case? Well, this infimum is equal to this supremum. That means that there must be some quantity here and some quantity here that get arbitrarily closer and closer, right? So for this fixed epsilon, we should be able to find a partition P1 such and a partition P2 such that UFP1 minus LFP2 is less than epsilon. Okay. Now it's easy to find a common refinement. So UFP1 union P2 minus LFP1 union P2 is of course less than epsilon. Why? Because by going to the common refinement, you're only going to decrease this quantity. Sorry, you're only going to increase this quantity and decrease this quantity. Therefore, the difference is only going to get lesser. So you have UF P1 union P2 minus LF P1 union P2 is less than epsilon. Okay, so this proves one direction. Conversely, assume that for each epsilon greater than 0, we can find P epsilon such that U f P epsilon minus LF P epsilon is less than epsilon. Then it follows immediately that UF is equal to LF. Why is this the case? Well, because UF minus LF is always going to be less than or equal to UF P epsilon minus LF P epsilon, right? Because this is the infimum of the quantities UF P epsilon and LF is the supremum of the quantities. Therefore, UF minus LF will have to be less than or equal to UF P epsilon minus LF P epsilon, and this is less than epsilon. So what we have shown is UF and LF can be made epsilon close, hence by a theorem which we proved way back in week 1 or week 2. I think week 2 we are done. Okay, so because UF minus LF is less than epsilon, we are done. So this was a rather simple criteria. In fact, it just rephrases the fact that UF equal to LF in a slightly different language. But this is very useful, as can be seen in the next theorem. Any continuous function f from AB to R is Riemann integrable. Now here is a situation where we will not just use continuity, we will use uniform continuity in the proof. So first of all, observe proof. Observe that f is bounded because it attains its maxima and minima. It's going to be bounded. We have already seen that the image has to be also going to be a closed interval. Observe that f is bounded and uniformly continuous. Okay, so what we are going to do is we are going to produce for each epsilon a partition p epsilon such that the previous criterion is satisfied. So fix epsilon greater than 0 and choose delta greater than 0 as per the definition of uniform continuity. This just means as a recall, this should be digested by you and flowing in your veins by now, but just to recall, if mod x minus y is less than delta, x comma y coming from the closed interval AB, then mod f of x minus fy is less than epsilon. Okay, so we have now got this condition of uniform continuity that sort of says that the moment points are close enough to each other, then the values are going to be close to each other also. Now this will immediately show that we can find a partition that we want. Let P be any partition, or rather let P epsilon be any partition such that each delta xk is less than epsilon. Less than delta. That just means that consecutive points in this partition are less than delta distance away. Okay. Now, what will this show? Well, let's compute UF P epsilon and LF P epsilon. Okay. This is just going to be summation capital MK delta xk. Here this xk looks like a subscript, delta xk, k running from 1 to n. Recall, capital MK is the maximum and this is going to be k equal to 1 to n, small mk delta xk. Now we have this. What we are really interested in from the previous criterion is UFP epsilon minus LFP epsilon, right? And a moment's calculation will tell you that this is summation k equals 1 to n mk minus small mk delta xk. Well, that was easy enough. Well, what do you know about capital MK minus small mk? Well, this is a continuous function. F is a continuous function. So consider f on x k comma x k minus 1. Okay, this is f on k xk minus 1 attains its maxima and minima. That means there are points in this interval xk minus 1 and such that f of that point is capital MK, and another point in this interval xk minus 1, or rather I reversed the thing, it's xk minus 1 xk, sorry about that, xk minus 1 xk. There are points in this interval such that f of that point is capital MK and f of that other point is small mk. We can find points here simply because this function is continuous and this is a compact set, therefore f will attain its maxima and minima. Okay, but that just forces by our choice of delta and the fact that xk minus 1 has to be less than delta, because we chose the partition that way. We must have capital MK minus small mk is less than epsilon. And the beauty of this fact is this is true for all k from 1 to n. Irrespective of the choice of k, this will have to be true. That just means summation k equals 1 to n small mk, I mean capital Mk minus small mk delta xk, this has got to be less than epsilon times summation k equals 1 to n delta xk. And just thinking what this summation delta xk is, you will be able to see that this is just epsilon times b minus a. This is just epsilon times b minus a. Now what we have shown is, given any epsilon, we can find a partition p epsilon such that uf p epsilon minus lf p epsilon is less than epsilon times b minus a by k epsilon principle, the previous criterion, previous theorem guarantees that f is integrable. Okay, so this completes the proof. The proof was an application of several properties of continuous functions. Please go through the proof carefully and see where each property of continuous functions were applied. To even begin the proof, we had to use the fact that continuous functions on compact sets will have to be bounded. We have defined integrals only for bounded functions. This is a course on real analysis, and you have just watched the module on criterion